These are the notes for lesson 6.9. We're going to be learning about symmetry. So hopefully you learned back in elementary school that symmetry just means you could fold something in half and it would be the same on both sides. So this first question says, draw in all lines of symmetry in the shape below. If there are no lines of symmetry, submit an answer without drawing them in. So just to pretend here, if I want to click and draw a line horizontally through F, does this upper top part look the same as the bottom part if I were to fold this over? No, so that wouldn't work. I couldn't do anything vertical like this because if I folded this over, this would go over to the left. So this is not symmetrical. This letter F actually has no lines of symmetry. So this is one where you would just submit it and you're done. Okay, let's try another one. So this little star here, I can just see right away that if I go from point to point, that then this right side would fold over and completely match the left side. I could also do horizontally to where this top would fold over and match the bottom. And then I want you to think about if I went from here to here. So now only focus in on this diagonal line. Is this point and this point, are they equidistant from my line of symmetry? So if here to here, the same as here to here. Yeah. And this little point here and this little point, is this the same distance here as it is here? And this point here to here, yes. So that's a line of symmetry. So if I can do it that way, I should also be able to go from this corner to this corner where, again, this point here, the distance it is from my line of symmetry is the same as this point is to the line. And you can just compare like that. So it should have those 4 lines. You don't have to be exact, but you have to be pretty close for them to count it correct. Okay, and then the next type of symmetry we need to talk about is called rotational symmetry. Rotational symmetry means if I literally rotate this shape, I need it to be itself again. I need it to be on top of itself. So rotational symmetry is anything less than 360, meaning I can spin it less than completely around, because if I spin something completely around, it's going to be itself again, of course. But less than 360 means it does have rotational symmetry. This shape is different because this side here, this top is longer than this side. So even if I spin it here, this would not match. It's only going to match when I flip this completely upside down to where that line would be on top of itself here. So it does have rotational symmetry. I can turn it less than completely one turn and it will be on itself. And so this is an easy one because if I flip something here to here, that's half of a 360. And 360 divided by 2 would be 180 degrees. I like that it lets you try it, so we're going to watch it spin and see how it's itself again. Let me do it one more time. So see how it's not itself until here. It would do it again at 360, but again, that doesn't mean rotational symmetry because then everything would have rotational symmetry. Okay, there it is one more time. So I take my 360 degrees, my total circle, divided by how many turns. Let's try another one. Okay, this one kind of looks like a bow or like a tie on a suit. This one, if I spin this here and think about it sideways, it's not going to map on top of itself. If I spin it upside down, since this point is longer than this point, even 180 degrees, let me show you, even 180 degrees would not work. So if you see it, see how now the longer point's here? So that's not going to work. So this actually does not have rotational symmetry because no matter where I spin it, it's not going to map or be on top of itself until a complete revolution. Okay, let's try one more, this little pinwheel shape. So see these semicircles here? This semicircle would, if it were here, would match up. So here to here to here. So you're kind of figuring out just how many points does it have symmetry. So here to here, there's 1, 2, 3, 4, 5, 6. So every sixth of a circle, it would map on top of itself. Well, 360 divided by 6 would be 60 degrees. Let's try it. So you can see there's 60. And there's another 60. Oh, it's not going to keep going. But every 60 degrees, it would be on top of itself. So we are correct. And there you can see it keeps spinning. Okay, and then the last thing that's in this section is very similar. The regular polygon, regular meaning every side, every angle is exactly the same. is to be rotated about its center. What is the minimum angle of rotation that would carry the figure onto itself? So we have to count how many sides it has, because every time this side would be on this side, it would map on top of itself. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we're simply taking 360 divided by 12. I can pull up this if you would like. 360 divided by 12, which should be easy, is 30. And that's our answer. Okay. Try another one with no picture. It says, which angle of rotation would carry a regular pentagon onto itself? And so I've got my shape, which is a pentagon. It has 5 sides, so I would have to take 360 divided by 5 sides. That means every 72 degrees, my shape would map on top of itself. Well, 72 is not here. So then I would have to keep, I can multiply by 2, keep adding 72 to try to find another one of these. Because every 70, oh gosh, didn't mean to do that. Let me do that again. So it was 360 divided by 5, that was 72, times 2. I'll just keep adding 72. 216, and I see it. The other thing that you could do is take these options, so you could try 315 and divide by the 72. If it comes out as a decimal, that means it's not a multiple, it's not a factor. So you could keep trying the other options to see if 72 divides evenly, and it doesn't, except for the 216. So you're watching it, so this pentagon is every 72 degrees, and you're just checking to see which of them divide by 72. All right, and then the last question, similar to that, a certain regular polygon, so again, meaning every side and angle is the same, is rotated 72 degrees about its center, which carries the figure onto itself. Which regular polygon could it be? So this is kind of a guess and check here. So we know 72 degrees. So let's try a triangle. A triangle has 3 sides. So let's do 360 in a complete circle divided by 3 sides. Every 120 degrees, a triangle would be mapped on top of itself. Well, 72 is not going to go into 120. It's not going to multiply to make 120. So the triangle's out. Let's try an octagon. So take 360 divided by an octagon's 8 sides every 45 degrees. Well, 72 is not going to divide by 45 either. 45 double would be 90. So no. Let's try a decagon, which has 10 sides. So we should know that 360 divided by 10 is 36. Well, I know that 72 does divide by 36 2 times. So it has to be a decagon. So basically you're just guessing and checking, trying each number of sides, 360 divided by those sides, and then seeing if it's a multiple of that number. And that's it. And you can watch it here spin. So every 36 degrees. So then the second time it would spin would make it 72 degrees.